Good morning, folks. Now, the first thing I want to talk about today is this video. This is an old video with a guy named John Shive, Dr. John Shive of Bell Laboratories.
People who study waves extensively in the various fields of physics and engineering are impressed by the similarities which exist in the behavior of waves in various mechanical, electrical, acoustical, and optical wave systems. These similarities are due, of course, to the basic fact that waves of all kinds behave fundamentally alike. These two rib-like structures are mechanical wave demonstration machines. With them, I can show you many of the various wave properties which you may have studied experimentally or theoretically, perhaps without ever having actually seen what the waves themselves are doing. The waves which travel on this machine are really waves of twist or torsion, which propagate along this central wire. Attached to the central wire are these cross arms, which translate the torsional motion of the central wire to the up and down transverse motion of the ends of the cross arms, which you see. The entire structure is supported in a set of bearings which permit the central wire to twist freely. This second wave machine is built similarly to the first. It has cross arms which are considerably shorter than those on the first machine, and as a consequence, the speed of a wave along the second machine is about 3 times faster than the speed of a wave along this machine. You'll see later on why I have these two machines. First, I want to show you the two different ways in which waves may be totally reflected. Observe that right now this machine has a free end. That is, this last cross arm is perfectly free to move without restraint. If I start a wave at this end of the machine, that wave travels down to the far end, is reflected there, and returns as a reflected replica of its original self. But now let me terminate this machine in a different way. I'll clamp this last cross arm to a heavy stand so that a wave arriving here can't produce any displacement of the cross arm. This time you see the wave is reflected upside down. The reflection is still total as it was before, but the wave is inverted upon reflection. In a mechanical wave system, then, there are two ways in which the total reflection of waves may take place. Right side up, if the reflecting end of the medium is completely free, and upside down if the reflecting end is completely restrained. Now, if nature has any consistency, and we like to think she does, this alternative reflection possibility should exist for waves of all kinds, and these other drawings here show that indeed it does. Take the case of an electrical transmission line, for example. You know that there are two ways in which electrical waves can be reflected, depending on whether the far end of the transmission line is terminated by a short circuit or by an open circuit. And similarly, in the case of waves traveling down an acoustic tube, there are two different reflection possibilities, depending on whether the end of the tube is closed by a rigid termination or by the acoustic analog of a free end. Note that in the mechanical situation, a clamp is a constraint preventing the displacement of the end of the wave medium. The electrical analog of this state of affairs is an open circuit termination on the end of a transmission line, preventing the flow of current at such a termination. And the acoustic analog is a rigid closure at the end of an acoustic tube, preventing the longitudinal vibration of the air. In all of these cases, the reflected waves come back upside down, and in all of these other cases, conversely, which are analogous to the case of the free end of a reflecting wave medium, the reflected waves come back right side up. You see, nature really is consistent. Well, now let's have a look at some of the other things we can do with our wave machines. One of the most important topics in the general development of wave behavior is the principle of superposition. when two waves traveling in opposite directions on the same medium, as you see here in slow motion, pass through each other, the instantaneous amplitude of the resultant wave is the algebraic sum of the amplitudes of the two constituent waves. This principle of superposition is equally valid when one of the two waves is positive and the other one is negative. Observe that in this case, at the instant of exact coincidence, there is a momentary cancellation of the amplitude, and the medium appears to be undisturbed. Now let's have a look at the superposition behavior of continuous trains of periodic waves. With this small motor and crank, I can generate such a train of waves at this end of the machine and reflect them back upon themselves at this end. All right, in slow motion now, here come the waves. After reflection, the waves travel back up the machine, superposing on the oncoming waves which they meet to produce patterns of built-up amplitude at some places and complete cancellation at others. The pattern that you see on this machine appears to be standing still, doesn't it? The various portions of the medium simply bob up and down in place without giving you the impression of motion in either direction along the machine. Observe that in this pattern, there are places where the medium appears to be standing completely still all the time. These dead spots, or nodes, are exactly half a wavelength apart. Now, I'm sure that you've all seen behavior of this kind before. For example, a vibrating string always vibrates naturally in one or more segments separated by such nodes. Now let me show you something else. Suppose I simply move this reflector a short distance up the line toward the generator, just far enough so that the travel time of a wave down and back is an exact multiple of the wave period. Under these conditions, the new waves which are continually being sent out by the generator superpose upon the previously emitted and multiply reflected waves in just the right phase to build up the amplitude to an abnormally large value, new crest on previous crest, and so on. The system thereupon becomes resonant, and the amplitude builds up to the noticeably larger value that you see here. Under these conditions, the new energy which is being fed into the system at each cycle is exactly equal to the energy which is being dissipated per cycle through friction at this new amplitude. Now, the initial adjustment which I made in the length of the machine to produce this resonant condition is called tuning. I could just as well have produced resonance by leaving the line at its original length and tuning the frequency of the generator instead. And I can destroy the resonant pattern that I have here by changing the value of either of these parameters a little bit in either direction. Another way of looking upon a resonant system is to regard it as a reservoir for energy. Thus, the escape wheel of a watch, a child's swing, a sounding organ pipe, the resonant circuit of an electrical radio transmitter are all examples of resonant systems. They exhibit abnormally large amplitudes of oscillation, and they possess relatively large contents of energy which have been built up by superposition over many previous cycles. Now, from here, I want to go on to the subject of the impedance of the wave medium. The generation of waves on a transmission line of any kind, electrical, optical, or what have you, involves two parameters: an originating cause and a resulting effect. In an electrical transmission line, for example, the cause of the waves is an AC voltage applied to...
Okay, so before we continue with this video, I don't want to play the whole thing. I just wanted to play that first 10 minutes, give people a brief introduction to John Shive and what the Shive wave machine and generator is and what it does. so they can see what we're building here. Now, imagine you had that same Shive wave machine that John Wave demonstrated, but you could extend the length of each one of those rods. So you know how he had the two machines, and the wave speed was triple on the smaller wave, the smaller rods than the bigger rods. What if you had a machine where you could actually just live adjust with a computer circuit right on it and a chip right on it? You could live adjust that length of the pendulum. You know, and so you could adjust the frequency of it live. You could actually drive it parametrically by changing that term, by changing the length of it. You can actually drive the pendulums and drive the machines each individually with these motors and the servo motors and the chips that we have set up here. We got an accelerometer chip, the power chip, and a controller chip, little mini computer that has a program that is running on it that was written by professor over here at WPI. And so we're trying to get some people to help out with this. This is a big project. We have 100 of these machines that we need to build, and this is just a small scale, like demonstration of about 10 or 12 machines on it. And so that's a big project. We're looking for some volunteers who are interested in mechanical and electrical engineering to help out with that project, because that Shive wave machine, as you saw, it's a great teaching tool. It's a great way to demonstrate how wave mechanics works. And if you have one of this machine, which we're trying to build, which allows you to change the length of the actual rods on the Shive machine live with the controller, you're going to be able to demonstrate even more wave physics, especially the important wave physics of parametric generation and parametrically driven systems, which is super key to understanding a lot of the science that we're going to need to break out of the current technology paradigm. So next, we'll get right to, since Curtis Horn is here with us in the audience, we'll use this opportunity to show off our demonstrations of the Charles Bueller machine. So right now we have a glass bell jar. I just used a mason jar with some vacuum epoxy glued to the end of a KF50 flange. And then out of there comes our vacuum sensor, which is connected to this machine right here, which will show, it shows 750 torr. That's atmospheric pressure right now. This is the power supply for the diffusion pump. I have to open up this diffusion pump and add oil to that diffusion pump. It's an AX65 diffusion pump. If anyone was wondering the make and model, it's go look that up. And it says it needs 30 cc's of oil, which is cubic centimeters. That's 30 milliliters. So that's 10 of these pipettes filled up to the 3 millimeter line. I don't know. I don't know where all the measuring tools are, but that's the best way I can do it. So I'm gonna use this to measure out 30 cc's of our vacuum pump oil to load up our vacuum pump and get that loaded up. That's one of the things I have to do. And then I got a couple other projects I'll just show you real quick so people will see what we're in for today. All the stuff I have to do at the lab this morning. Got 3D models printing right now with the open air version of the Charles Bueller gravitator experiment. So this is like Biefeld Brown's gravitator, only it's enhanced and perfected through a lot of trial and error and generations of building these things. So basically what we have is a two-part plate system. Plate, I don't know where the plates are. So these are a bunch of the holders. We have We're going to have wires. You see the slots in there for the wires that are going up. We're going to wire to every other one so that every other one's ground and every other one is hot. So I have the slots in here to run the wires. I gotta build the wires for that because it's going to be high voltage. And then the connection points are going to be on the slide itself. It will have some copper tape that we'll put on the slide itself, and the copper tape will make contact with the electrode here inside the slide piece, so that when we slide them in, alternating, you know, back and forth in these slots, that they'll get powered up to either ground or hot, vice versa. Now, on these slides themselves is a bit of engineering handiwork, and that's going to be these. That's going to be these things. So, if you see what we did here, we wrapped the channels with foil tape, and then I cut off the surface, shaved off all the tape off the surface so that it's bare on the surface, and you just have a whole bunch of these long U-shaped copper tape channels. So they're conductive copper tape channels, and they're very long, U-shaped, and those are going to hook up to electrodes on each end, which will the U shape will go, and then there's another solid plate on the back where so that it's kind of like the Biefeld-Brown effect lifters, where you have the anode and cathode. There's just going to be a hot, and then it's going to be attracted to these plates, and then you have 8 of those, of course, stacked in alternating alignment in this open air tester thing. And then we can wire this up with the open air tester and see if we get any gravitator force out of it. So that's the open air gravitator test. And then we have another version I'm building with these fins that are going to be all assembled on this little carousel type wheel. Let me get all the parts for this so I can show it. So inside of here is going to be what's the other piece? You don't see it here. I thought it was here. This piece is on top inside. It's glued on the top of the mason jar inside of there. And then this piece fits inside. It's a little spin balance. And then that sits on another wheel device. So it's very low friction. And this red piece will be allowed to spin. And then on that red piece, we're going to mount some gravitators, hopefully thin enough to fit inside this bell jar. It needs to be real thin, but we want to get maximum surface area, so we're going to take advantage of the vertical, the room we have vertically rather than side to side in that bell jar. We're going to make 2 of these little rotator things balanced on each side. That one's powered from the wire on the top right here. So the wire on the top will power through there, down through the middle. And then there'll be another wire coming up from the bottom, the ground, which will power the other sides of the 2 electrodes on these this carousel wheel piece, which will spin, and with the ion wind or whatever the force generated, if it's a gravitational force and not ion wind, then of course it will work in under high vacuum, which is what we're going to try to test today. So let's make sure this is good. There we go. Look at that pressure drop. come on and suck, suck, suck. Let's see how low that pump can get with, this is the old vacuum pump sensor. We went through 2 of them that didn't work until we finally got one that did work right here. The Intercon. So yeah, that's that will suck it down to closed vacuum, and then we'll get once we get the vacuum pump up and running. I'm gonna let it repressurize again. That way I can open up this flange right here. I'm gonna put some gloves on for all that, because even the oils on your skin will contaminate the whole vacuum and screw it up. So you gotta clean everything with isopropyl and then wear gloves. Yeah, we didn't put the oil in yet. I just wanted to demonstrate and show it. So, so they got that going on. Let me see what else. What else we have here coming up next. Oh yeah, this is super cool, guys. You're gonna freak out with this one. So. This. Do you know what this is? This is our spatiotemporal optical vortex cannon creator. And it works. It's got the cones inside. It's got 2 cones. So this is a positive negative on the inside cone, and then there'll be a positive negative here. So negative, positive, negative, then the inside cone will be negative, and then a positive cone on the inside, which I was trying to make with this tinfoil thing, but I want to make something more solid metal that I can solder together and put on the inside of that inner cone. It, of course, connects to a coaxial cable piece on the inside there, so we can power this thing. And this is from Sabina Hosenfelder's video with the flying donut pulses, and this was I modeled this in 3D modeling from the pictures I posted on Twitter that came right from the paper that she did that video on. She had posted the paper. I had reached out to the scientists Wang and Shen, who wrote the paper, to try to get some more. I'm going to send them another message with some pictures and video of the setup I have so far. I'm going to glue that inner cone to this kind of spacer piece so that all this stuff can be held together in the right space. And then, of course, we pump this with a sine wave, a sine wave with the alternating opposite sine wave on the inside cone. And the outside cone then will produce, an electric field will go this way, inside, back, and then it will alternate back and forth, making this toroidally shaped donut pulse. And then with the inside cone, we'll create another mini donut pulse for the inside piece. It's kind of like when you blow a smoke ring, you have the outside part, and then you have to blow the inside part of the smoke ring to get to create that torus effect and that topologically stabilized field geometry, which is not well understood. We don't know what these things do, and I don't want to point it at anybody or anything. In fact, I don't want to test this thing until we can don't even power this on or test this until we can get down to Mark's lab and have a Faraday cage, because I really don't want to be around this thing shooting flying magnetic donut pulses at me through the air. I don't know what that might do. So, but cool nonetheless. I'm going to see what that does, and I'll post all the. We're going to have a GitHub page. We have a GitHub page, where we're just working on modifying all these files and getting all the prints perfected. I don't want to. I want to get everything perfect and working right before we share that, and then we'll post up a whole thing on how to do it on Facebook, so other people can replicate and try it, and try this technology themselves. So the idea is that some of this might produce a thrust. The idea is that maybe, possibly, if there's, gravitational fields that are created in the collapse of this, that this might be like the M drive and produce a thrust. So that's the hope and idea, is that there might be some gravitational applications, and then it becomes an issue of engineering a design better than this for producing those spatiotemporal optical vortices. So that's up for the engineers and the other people in the group, and we always welcome the skeptical people and the scientists who know better to come and show us where we're wrong and how to do things better. So that's how we grow this group and continue with the science. So I got those projects going on. Let's maybe we'll pop this open and work on this. You guys want to stay? Should I stay live and just let you guys watch me do boring work? Because this is like the fun part where I show off everything, and then I'm gonna have to go and actually do like work on this stuff. So maybe I'll keep it live so you guys can see the what really has the frustration and all the in all of its glory. Yeah, we'll leave it on for about now for another half hour while you guys watch me change the vacuum oil pump. You can do that. We're also streaming on Twitter and Twitch. I'm going to end the Twitter stream, so people have to, because Twitter is more of a short kind of thing. So if you're watching on Twitter, you'll have to jump over to YouTube, Alien Scientist YouTube, or OG Alien Scientist on Twitch. So see you guys over there. Thanks for watching. No, we're just going to remove that destination from the stream. So we're still streaming live on YouTube and Twitch. We lost about 150 viewers on people that were watching on Twitter, which is cool. Fine. I'm going to open this up. And I won't be able to talk while I'm doing this because I don't want to risk contaminating our vacuum setup with any foreign contaminants. So it's open that valve. So pressure before I can do that. And there, we're back to atmospheric. This KF50 clamp off. This is not going to be too viscous to get a good fill on that. I'm going to get a better measurement tool for this. Better measurement tools. Well, I can't find any graduated cylinders here, and I'm just going to have to go down to there. That's 3. Back up. That's another 3 milliliters. That's 2. That's another 3 milliliters. That's 3. That's 4. That's 5. That's 6. That's 7. That's 8. That's 9. And that's 10. All right. We're just going to test the vacuum. I still have to build the carousel wheel and all that stuff, the setup that's going to go inside of here. And then I'll have to take this off. And the way I have this designed is this piece. I made this piece. It'll have a long stem on it. This one broke, unfortunately, but this piece fits inside the middle of the KF50 tube. And that way it's adjustable up and down to get the height right. So we'll be able to mount the wheel and everything on top of that, and then push that whole assembly up inside through the tube and into the bell jar for our setup and apparatus. So, all right, now that this is connected, I have that set up. I'm gonna tighten this back down. Put that cap back on nice and tight. And then we can power up the roughing pump. Sounds a little rough. Let's start it. And we're going to let that just get it down. We're going to let that run for about 8 minutes or so and let it get down to a high enough vacuum where we can turn on the turbo pump, diffusion pump, and all right. Oh, that's cool. I'll let you know. I'm using OnShape. Here, let me go back and I'll share some of the stuff with you with the CAD work, so we can talk about that. That's fun. So we just got a freeware program. It's called OnShape, and I'll bring it over to the screen so you guys can check it out. Here we go. Share. Boom. Let's reconnect. So here's the design I have built. This is OnShape, and it's good because we can share this stuff. You know, people can actually, look up stuff on there and find it. SW, all right, that's cool. Well, whatever is clever, because this one we can share, and like I can go and change stuff and edit parameters and stuff, and go back and change things, which is sometimes easier said than done. Sometimes it's a little difficult to change stuff. But yeah, so this is the propellantless drive that we have working on. I also built this kind of roller machine to roll the metal to get it to fit inside the slots right, but it didn't quite bend them the right way. You have to adjust the geometry of these rollers in order to make it fit the inside of this geometry. We'd also experimented with making a tool to push the foil inside the grooves and get it evenly in the slots, but it didn't seem to work as good as the other method that I use, which again I might as well show you guys that method now. See if anyone has any suggestions for how I could do this better. But we'll see. Let me know if you have any better ideas than what I'm currently doing. But let me demonstrate. So we want to fill the gaps in this with this foil tape. So first thing I do is I measure off a piece about that long, and then I cut it. And then I peel back just a little bit of the tape to expose. It's really hard with the gloves on, man. I've been doing it without the gloves on. I don't know how we're gonna, maybe probably just have to build it and then wash it with the alcohol afterwards to remove any oils. But it's just so hard to do anything with the gloves. And the way I do it is I just start like there. I like to fold it back with a little bit and then just get it started. And then I use this. You guys can see the method here. Pull back on the foil and I push down into the first slot there. Whoops. Push down to that first slot, and then I slide back into the other slot, so it pushes the seam and tape across the bottom into the other corner, and then I come up the wall, up that side wall onto the top. When you're down flat, I go across and into the next groove, which I went over 2 grooves there. So you got to pull it back. And if you do it soft, it'd probably be easier with like a plastic. Get a plastic flat edge instead of this metal one, because the metal one seems to cause too many problems. But yeah, that's the basic idea. You get the foil on there, and then you seal it all down inside the gaps, and then you want to make. So I don't know. I don't know if I like this idea, because the MIT plane that they built used a little bit different idea, and then they just took a whole bunch of individual sticks of balsa wood and wrapped the balsa wood around 3 of the sides, and then cut it on the bottom, and then you take a bunch of those balsa wood sticks and you line them up in a stack. That way, there's air gaps between them too. But I don't know. This is the way Michael had set me up to do it, and then the final step to create that U channel is to carve off the top layer there. So I use this handy long blade scraper to just go down the seam, and it just shaves that tape off on either end pretty nicely, and then you have the finished product right there. So that's the method that I kind of came up with, just messing around, building them by hand. Of course, these are all like the all these pieces are the 3D print rejects, so I can play around and with them just to show you guys. Everything here is kind of being perfected, and once we get it all perfected, we'll have the 3D models available on the GitHub page, so people can print out their own on their own 3D printers, and then get some foil tape and build these things really cheap themselves. So this has been running for about like 5 minutes now, and we're down to 1.4 to the -1, and it doesn't look like it's moving off of that too far. I should turn this vacuum pump on now and try it out. Well, let's give it a shot. I need to. This is the fan that I've wired up for it first. So the fan's wired to here. Let's make sure the fan works first. Okay, the fan is on and working. That way we can keep this thing cool. Let's try it out. I don't know if I should keep sucking it down harder than that, or probably needs to come down a little bit further before I can turn the vacuum pump on. I don't want to mess anything up. But if we can get down to -6 torr, that's what we need for a hard vacuum to really show that the experiment works and without air. And if it works without air inside that vacuum chamber, right? That's huge. So we'll have to call Jesse Michaels and get Jesse Michaels to come fly out here and document it. Either way, even if it doesn't work, if it does work or it doesn't work, it needs to be documented and shown. Yeah, it's sorry, I'm not got to see what you're talking about. Winter Garden. Yeah, that was a really cool, the Winter Garden stuff that Jared did and got a hold of all that stuff. It's just great getting all these people from the community who've come forward and gotten tons of information that would have just been lost to history. This stuff was a lot of this work was classified, and then people were just never allowed to talk about it. And for us to go and find all these scientists and get them to come forward and share the information with this community, it's really helped preserve so much of this lost history for the public, for everyone out there to see. You know, we're doing proper journalism and reporting on this stuff so that people can say, hey, look, we spent tons of money and we wasted a lot of time on stuff that didn't work, and here it all is, and here's the proof that it didn't work, so that you don't waste your time too, and you don't think we're just covering stuff up and hiding technology, because that happened a lot too. They would say something didn't work and ridicule anyone working on it. Well, they're secretly researching what they told you is crap, and you're crazy for even thinking about. And that's that's some interesting stuff. So we got that going on. We got the bismuth nanoparticles. I showed you that. We're trying to get we're trying to make the bismuth magnesium layered materials. The best thing we could come up with is getting we got this 3% zinc magnesium alloy, which was matches their layer pretty good, and then we actually chemically deposited the bismuth onto the magnesium with bismuth chloride and electrochemically plating it. Actually, I don't even think you need to electrochemically plate it. You just need to put the bismuth chloride on the magnesium, and it will chemically deposit right there. So yeah, nobody records the failures, man. We need to record the failures and document that and show it. It's failures are a big part of the science too, and it helps other people not waste time on stuff that maybe doesn't work. So what else is going on here? Yeah, I wish we could get some more people locally to come who have the right. Send me your resume. Send me, we take a particular towards WPI students, because WPI were the Worcester Polytech were the ones who started this whole the Shive Wave project here, and it's a WPI professor who designed and programmed all these boards. So if you're a WPI student, or you know anyone who's a WPI student who's interested in helping out, have them send over their resume. If you're a WPI student, it's pretty much guaranteed that we'll take you. Whereas if you're a MIT or Harvard or whatever you want to get involved, reach out to. We're always looking for more reliable help. So this is the Shive wave generator machine. So I showed that video. In fact, we can go back to that video and play some more of that. This is the Shive wave machine.
The input end of the line, while the result is an AC current flowing into the line. The ratio of the cause to the effect is called the impedance. You're probably most familiar with the term impedance through your studies in the field of electricity. But this impedance concept is just as applicable to wave systems of other kinds as well. On our mechanical wave machine there, for instance, the cause of the waves is the oscillating torque which I apply to the first cross arm, and the result is the oscillating angular velocity imparted to the medium. On that structure then, the impedance, the mechanical impedance, is the ratio of the applied torque to the resulting angular velocity. In terminating the other end of a transmission line, we frequently seek to adjust the impedance of the terminating load to equal the impedance of the line itself. When this is done, all the wave energy traveling down the line is absorbed by the load, and no reflection takes place. The load is then said to be matched to the line. Now, this matching condition can be demonstrated very nicely with the wave machine here by attaching to this last cross arm a mechanical impedance and adjusting the resistance, the counter torque, with which that impedance reacts back on the motion of this cross arm. Such a mechanical impedance is afforded by this dash pot, simply a tin can full of water with a little piston pumping up and down in it. By sliding this dash pot in or out along the last cross arm, I can control the counter torque with which it resists the displacement of the medium, and thus match the impedance of the dash pot to the impedance of the transmission line itself. When this adjustment is properly made, the dash pot absorbs all the wave energy that travels down the line, and as you can see, hardly any perceptible reflection takes place. Now, instead of using single waves, suppose we have a look at this behavior with a train of continuous waves. Here you see such a train of waves traveling down the machine from the generator to the load and disappearing into the dash pot. Now suppose I spoil this nice matching adjustment by moving the dash pot farther in toward the central wire. The impedance of the load now no longer matches the impedance of the transmission line, and a partial reflection of the wave energy occurs. Let's have a look at this partial reflection now with continuous waves instead. We expect some kind of standing wave pattern to appear on this machine now, don't we? After all, we have running waves going in this direction and returning waves coming in this direction of the same period on the same medium, only this time the returning waves have the lesser amplitude because the reflection down here is only partial. Well, I do see a standing wave pattern of sorts. Here are the nodes, half a wavelength apart. Only notice now that the nodes are no longer standing still, as they were in the case of 100% reflection. Suppose I have the camera speed up the picture for you so that you can see what the envelope of this standing wave pattern looks like.
Yeah, so this is the Shive wave generator, and what we have is a Shive wave, a generator that you can actually adjust the length of the pendulum of the swing arms, real time with the computer. Each one of these has an individual ID chip and a controller for them, so you can actually like individually change the length of the pendulum arms on the Shive wave machine, and that's what we're trying to build. One of the many projects where we've got going on, because that will be amazing for demonstrating how parametric generation and oscillation works, which is key to understanding, you know, some of these other quantum processes. So yeah, it will be cool. It'll be awesome once it's done. This is a kind of a video on this would be like Veritasium should come and do a video on this, because the video on this kind of a thing, this project should get millions and millions of views. This is like the ultimate nerd machine. So we're going to have 100 of these Shive wave machines. Each one of these machines represents a bar on the Shive wave machine here. So each one of these bars on the Shive wave machine, each one of these is one of these machines, and the machine will allow you to change the length of the bar in real time while demonstrating the machine. Oh, I know, it would be nuts, dude. So we have to do it. We have to get it done and show it off. I just need help, man. I can't do. I have so many other projects that we're trying to do on a time schedule. I got 2 weeks to get this Charles Bueller thing done. This was supposed to get done over the summer with the interns we had, but we got caught up with the vacuum pump stuff on a lot and dealing with a lot of other problems that we just didn't have time. So if anyone is local and wants to help out, please send us your resumes and stuff. So for sure. Yeah, it's super cool. Anyways, guys, thanks for watching, and that's pretty much all I have for you today. I gotta go and oh, look at this. We're down to 7.8 to the -2. Not bad. I think we can get down to about 2 to the -2 if we run this thing long enough, and then we can turn on this vacuum pump. Let's try it out. Yes, it is running. Uh-oh. Something's not right here. We just lost pressure. Anyways, I'm gonna mess around with this, guys. I gotta call Mark and get some more help with this. And yeah, if you guys yeah, I know that glass. There's that glass jar there, man. I should be wearing eye protection in case anything happens to that. Get my eye protection on. All right. Now I'm totally safe. All right, guys. Wish me luck. Well, you can go look it up. What do they cost? It's a, give me a second. Share. We'll go look it up. AX65. Oops. Oh, that's about $2,000. Maybe, $2,500 brand new. Yeah, look, you can buy one right here, $2,500. All right, that's what it costs. But that's a poor man's setup, man. If you want to, I mean, you guys saw the setup that Mark had? You guys see Mark's setup? Let me just bring up a picture of Mark's setup real quick so people can see that. Oh boy. Come on, Mark. Where the heck is it? You just posted it yesterday. I'm just going to find it on his page, man. Falcon Space on Twitter. Media. Oh, yeah, right here. All right, let me share this so you guys can see. It's going to be pumped. Look at this. Look at that bell jar, man. Look at the size of it. That's like one of those big air blowers, the floor blowers. That's the size of the vac. 14-inch bell jar, 14 inches across, man. That's wow. That is a beauty. And then he's got this whole vacuum setup, some turbo pumps, hoses, and yeah, that's what I'm competing against right now, man. Like the difference between a poor man's $3,000-$4,000 setup compared to like a $30,000-$40,000 setup that Mark's over there working with, man. So cool. So cool. Anyways, thanks for watching, guys. Go follow Falcon Space Labs and follow me on Twitter, Alien_Scientist. So thank you all. Have a good one.